In the previous video, we tested a 10 ampere-hour lithium titanate cell by Varicore. Today, we will focus on building a 12-volt battery. We will answer the question of whether a 6-cell or a 5-cell battery is better for a 12-volt setup. Lithium titanate is amazing for its lifespan and power, but its unique voltage means neither setup is perfect. Let's break down the pros and cons so you can choose the right one for your build. For the construction, we will use dedicated battery holders and reinforced tape to ensure the cells stay put, and JK-BMS with a 0.4 amp active balancer and maximum load of 40 amps. Before assembly, the battery is charged to 14.8 volts. Here you can see the battery cells being secured using reinforced tape. First, we will install the temperature sensors. Running battery cells without a BMS is a huge mistake. Here is why. Without a BMS, cell voltages will drift apart, quickly ruining your pack's capacity. You also lose protection against overcharging and deep discharge, which can permanently kill your cells. The temperature sensors connect to BMS here. Another connector is used to connect the individual cells. Connecting each cell is crucial for effective balancing and battery monitoring. Starting from the left, the main negative terminal of the battery, then the positive terminals for cells 1 through 6. The final wire also connects to the positive terminal of the 6th cell, which serves as the main positive terminal. It's also important to ensure the cables for each cell are the correct length. We'll finish the end of every wire with a proper ring terminal. Before connecting the BMS, we check the voltage in the connector to ensure it is connected to the battery in the correct order. As we move down the balance leads, you can see the cumulative voltage rising cell by cell. Now, we will charge the battery to 16.8 volts, which is the maximum, meaning 2.8 volts per cell. The battery is now charged. Here we see the battery just before its first full charge. The cells are balancing, and we can monitor their individual voltages. As you can see, we are running a 6-cell setup here. Once the cells hit the 2.8 volt limit, the BMS will cut the power to prevent overcharging. As we hit the end of the cycle, the voltage starts to climb much faster. Now we can see the charging curve. After that rapid voltage spike, we can see that the overall charging curve for LTO batteries is actually relatively flat. After a while, the cells in the battery have balanced themselves. The difference between the cells is only 4 millivolts. Now, let's look at the battery management system settings. We have 6 cells, and the balancer is set to 5 millivolts. The cell balancing starts at 2.6 volts, and the maximum balance current is 0.4 amperes. The cell overvoltage protection is set to 2.8 volts. The required charging voltage is set at 2.795 volts. A 100% charge is reached at 2.79 volts per cell. The cell overvoltage protection reset is at 2.785 volts. The cell undervoltage protection reset is at 1.55 volts. A 0% charge is at 1.51 volts per cell. The cell under voltage protection is set to 1.505 volts. The battery shuts down at 1.49 volts per cell. The continuous charge current is set to 20 amperes. We can see that the charge under temperature protection is set to minus 20 degrees Celsius. This is an advantage of this type of battery. Now we will start the battery discharge test. We are discharging with a current of 5 amperes down to a voltage of 9 volts. Here we can see how the battery is already almost discharged. The discharging will end when one of the cells reaches 1.5 volts. In this case, it is cell number 5. The battery voltage drops sharply at this stage. You can see a large difference between the cells during this phase, about 0.5 volts. The battery generated 10.4 ampere hours and 153 watt hours. Here we see the discharge curve for the 6-cell battery. In the graph, you can clearly see how stable the discharge curve is for this 10 ampere hour battery with a constant 5 ampere load. Now we will try to charge the 6-cell battery using a car battery charger. The battery is charged to 14.6 volts and is balanced. We discharge at 5 amps. Here we can observe the rapid voltage drop below the 13-volt threshold during the discharge of the 6-cell version. We only get 2.5 ampere hours from the battery, which is only 25% of the usable capacity. That is not enough for my project, so we will build only a 5-cell battery instead. Now we will charge the 5-cell battery to its maximum again. In the initial cycle, the smart charger supplies 10 amps, and we see only 5 installed cells. Now the battery is just before being fully charged. The maximum cell charge is now set to 2.75 volts. The graph illustrates the charging process of a 5-cell battery with a standard 10-amp vehicle charger. On this graph, you can see how the smart charger reduces the current to 7.3 amps at 13.3 volts and to 4.8 amps at 13.5 volts. Now we see the discharge curve. It makes no sense to discharge the battery below 11.5 volts. We got 10.3 ampere hours and 128 watt-hours from the battery. The overview shows that for standard use in a common 12-volt system, a 5-cell battery is more advantageous. However, in the case of a car battery, there is a risk of overcharging the 5S pack by the alternator. Although the BMS acts as protection, it is not designed for constant cycling at those limits. On the other hand, a 6-cell battery has too high a voltage to be practical. It is not sufficiently charged by a common alternator and provides just 25% of its capacity. The lithium titanate battery is suitable for solar panels in sub-zero temperatures. Thank you for watching.